Good day. I'm Bruce Williams with Natural Resources Canada, and today I'll be talking about the fracture response of a TC1288B steel. This is a steel used for tank cars in the transportation of oil, but a lot of what I talk about will have applications to pipeline steel and other fracture of metals. I'd just like to acknowledge my co-authors at Natural Resources Canada, as well as our collaborator with the Transportation of Dangerous Goods program at Transport Canada, who is the regulator. At Natural Resources Canada, we study materials issues related to energy, pipeline, nuclear, transportation. So mainly what I want to talk about is developing a finite element model. It's very expensive to do large-scale tests. And so consequently, we want to have a very robust finite element model. Particularly, it has to have a lot of temperature influence from minus 80 degrees Celsius to 24. So we have to worry about the ductile to fracture response of the material, and we can be anywhere from quasi-static to dynamic rates. And so really what we want to do is develop that FE model and validate it just using Charpy V-Notch responses. It's kind of a way to minimize the amount of mechanical testing to validate the model. So what we see here is that there are actually two types of failures that we're worried about. One is the high temperature failure. Say there's an accident, the oil can catch on fire. That leads to degradation of the tank car. And so we're worried about the creep response in that case, 550 to 850 degrees Celsius. But what I'll just be talking about here today is the low temperature response from minus 80 to 25 degrees Celsius. And in that case, we're worried about fracture. We have to worry about the strain rates as well. If we consider an impact or a crash event, that strain rate can vary maybe about 10 to 100 strain per second. So what we see with TC1288B is a pretty typical response for steel alloy, where we see the typical Charpy ductile-to-brittle response at minus 80 degrees Celsius. It's pretty much brittle. And then we get a varying response. And so by room temperature, it's pretty much ductile. And what we have to worry about in the FE model that we're developing is that we have to capture brittle fracture when it's preceded by ductile fracture. So all those intermediate temperatures, you have brittle fracture, but it's preceded by ductile fracture. And so we have to capture that in the model. And so this is kind of what I mean here. If we just, instead of looking at the energy absorption, we look at the load displacement response, we get a lot of ductile crack growth as the Charpy specimen is deforming. And then at some point, we just get brittle cleavage fracture in the material. This is the response of minus 20 degrees. So we have to capture this in the model. So in terms of strain rate, we can measure the quasi-static versus the dynamic response. In this case, we just show Charpy tests. Everything else is exactly the same except the strain rate. One is quasi-static. The other is about 100 strain per second. And we can see a difference in both the loading response, but also in the basically the amount of deflection that the material handles before it fails. And so we have to capture the strain rate sensitivity of the steel in the models. And so the normal way to do this would be to do a lot of split Hopkins bar testing for the high rate behavior. But steel is fairly general. This steel is pretty, could be comparable to pipeline steel. So in this case, what we did was we just used the response of pipeline steel to represent the TC1288 steel. And so there's a slight variation of the strength with temperature for the quasi-static, which is the light gray that we see here. So as we decrease the temperature, we just get a slight increase in strength. But when we go to a stress strain of 100 strain per second, we get a much larger strength of the material, and this allows you to absorb a little bit more energy. And so using behavior of pipeline material. We're using that to essentially simulate, or we're using that to simulate the response of the TC1288B steel. And this strain rate effects are pretty well captured for steels. So now what I'll talk about is the ductile fracture model. We're using the Modified Mohr Coulomb model. This model was published for room temperature and one strain rate, Paredes and Wierzbicki. This model, without going into a lot of details, is a function of stress triaxiality and load angle. During crash, we expect the material to be subject to quite a wide range of variety. And so the key is that to calibrate the model, you have to do tension, notch tension, shear specimen geometries. You also use fracture geometries, single edge tension, compact tension specimens to help calibrate the model. And so extensive experiments, then you do a lot of simulations, say if you want to predict the triaxiality and the load angle. And then you use a number of optimization methods to come up with the material model. And so a lot of extensive work goes into calibrating and validating the material model for one temperature and one strain rate. And so really a question in this work is, can we take that well-developed model and just vary it a little bit for different temperatures, for different strain rates, and all we have to calibrate it is a tensile test and a Charpy test. And so that is kind of the question. There's 7 damage models, 7 coefficients in the damage model that we have to worry about. Can we simply vary them and still capture the experimental response just from a Charpy test? So simulations in this work, 24 elements through the thickness, very fine mesh, 0.2 millimeters, which is what Paredes and Wierzbicki used. So that way we can eliminate mesh sensitivity in the model. 32,000 elements, which is a reasonable size. We're only considering isotropic deformation and fracture, even though we saw in Charpy tests that the anisotropic, there could be, or this alloy displays anisotropic fracture. We're not going to consider it in this work. We use Abacus a lot for our models, but because we're running a number of simulations, we like kind of the open source code. So we're using Dyna3D, which is been around for many years, 30 years. It's the original version of LS-DYNA before it was commercialized. So in terms of, we're varying these 7 model coefficients until we match the experimental response, and we can do that reasonably well. We can capture the quasi-static and the strain rate response of the material without too much effort or too much change of the model. We can capture that response. So that was the quasi-static versus Charpy or dynamic response. In this case, it's all dynamic and it shows the influence of temperature. Again, we can maybe some under prediction here of the energy absorbed at room temperature, but 0 degrees, minus 20, minus 40, minus 60, minus 80, we're doing a reasonable job to capture the experimental response. One aspect that we are not capturing, particularly when there's brittle cleavage fracture, is we are not capturing the sudden load drop in the material. No matter how we change the coefficients, we're always getting an increasing energy with increasing displacement with the ductile damage model. And so really what we found is the ductile damage model. Just want to talk a little bit about the MMC failure surface, which is a 3D surface, a function of triaxiality, and a function of normalized load angle, which ranges from -1 to 1. Effective strain on the vertical axis. We have initiation surface that once we initiate the damage, the strength in the element is weakened until it reaches a failure surface, a failure damage level, and then the element is deleted from the simulation. Often present this as a 2D plot. In this case, at a normalized load angle of 1 and the final failure curve. There are 2 curves presented here. One is the original quasi-static room temperature result published in literature from Paredes and Wierzbicki, and then the TC1288B steel studied in the current work at room temperature in quasi-static. And this just shows that the model can be easily adjusted for different grades of the material. to account for slight material variances. How temperature affects this response. And so again, what I'm just showing is I'm just showing for one load angle, but keep in mind it actually can vary with load angle. And what we see is that we can get, as the temperature in the material decreases from 24 to -80, we can just adjust the parameters in the model slightly to capture the experimental response without significantly changing the fracture behavior of the material. At -80 degrees Celsius, it's really the light material here, is very brittle response. Maybe there's quite a gap here. Maybe it's not that realistic, but just remember that it's very brittle once we get to -80. Essentially, there's no ductile fracture at -80. It's all brittle fracture. Okay, so I sort of mentioned this. This is the response at -40 degrees. One of the issues with the ductile fracture model is that we always get a stable crack extension. We never ever get the sudden load drop that we see in experiment. And so what we see is that our ductile fracture model just could not capture brittle cleavage fracture. So we had to just wanted to make a simple adjustment to the model in order to be able to capture brittle fracture. So in literature, we often know the Berenian or the Baramin model, which describes the Weibull stress, is basically you're computing the stress around the crack front or in the plastic zone, and that is used as a measure of when the material will fracture. One of the issues is in a fully three-dimensional finite element model, it's difficult to actually describe the plastic zone because it's fairly complex. And so in this work, what we just did is rather than taking an average over the plastic zone, we just took the maximum principal stress in the damage zone. And if that maximum principal stress exceeded a specified value, you would get brittle fracture, and thereby we could capture the load drop in the material, which I'll show in the next slide. Just to note, there is a probabilistic nature of this. We know that brittle fracture, it can vary a little bit. So what we find is the brittle stress decreases with decreasing temperature by this nice linear response here. But I also want to show, I just put a little error bars on the brittle stress values, which vary from about 18 to 2600 MPa. But we do expect a bit of variation in the stress. This is like a Weibull distribution where we can get a little bit of range to predict the failure response in the material. This is just a little simulation. This is the ductile growth, crack growth that we see here. And then essentially when you get brittle fracture, the material suddenly fails. And that's what we want to capture here. I'm not showing it for all cases. There was no brittle fracture at room temperature and -80. It was all brittle fracture. These cases, though, in between, what we're seeing is we're seeing a large ductile crack growth and then brittle fracture. So at here 0 degrees, at near the very end of the test, we suddenly get a load drop. At 0 or -20 degrees here, we suddenly get the load drop in the material, the brittle fracture, very similar to experiment, as well as -40 and -60 degrees. So we're getting brittle cleavage fracture prediction preceded by ductile crack growth. And so that's essentially the summary of the model, that to capture, we can apply this FE model now to very large scale FE simulations, but we wanted to make sure that it was valid for a range of temperatures in a range of strain rates. What we showed is that we can take a model from literature in which a lot of work was done to calibrate that model, and then just tweak it a little bit, and we can still capture this wide range of material. And in order, just to say that to capture brittle fracture, we just did a little simplification with maximum stress in the model. When it exceeded a certain value, that triggered brittle cleavage fracture. And just like to acknowledge our regulator in Canada, Transport Canada, that takes care of dangerous goods, as well as many useful discussions with our partners, both at CanMet Materials and Transport Canada. Thanks for your time, and I hope you enjoyed the talk. Thanks.